Before we start the lecture today, I just wanted to announce a change regarding the feedback on Piazza. So as I, mentioned before, very briefly, so the original plan was to have everyone submit a feedback before each lecture for last lecture. But since now I think most of the comments, I've received most of the comments, they're very helpful. So I don't think we need a frequent feedback per lecture anymore. So I don't know if our TA has already made an announcement. So I plan to have everyone submit a feedback whenever you feel there is a need, or every 8 lectures from today on. So basically what I mean is you don't have to submit a feedback for every lecture, but you're still welcome. Okay, yeah, someone said Tia has already posted this. I just wanted to clarify. So you're still welcome to post any feedback. Also, you're welcome to take notes about your feedback, and if you wanted to just give me your feedback, a collection of your feedback for multiple lectures once, that's fine too. So basically, you don't have to submit a feedback for every lecture anymore. Okay, so any questions regarding that before we get started? Okay. All right, so I will use my iPad again to.
Are the slides for this lecture up on the website?
Oh, that's a very good question. So unfortunately, no, but do you guys prefer to have the slides first?
Yes.
I would prefer them because I annotate them when I'm
Okay,
in class.
so let me see. So is TA in the class? I could try to share in the Google Drive.
Yeah, I'm here, Dr. Hall.
Oh, okay. Awesome. I'm gonna share this to the Google Drive.
Okay. Yeah, I checked right before class and saw it wasn't up to upload anything.
Okay, yeah, thanks. I didn't upload it. So let me do that. Just a second, I need to save it to a PDF. Okay. All right, so now I will upload it. Okay. So,
Okay, I'll upload it to the website.
Okay, thank you. And you could also try to paste the link or something. Okay. All right. So let me try to share my screen.
For the students, I'll put it in the chat so you guys can get to it right now, but it'll also be on the website up in like 2-3 minutes.
Okay, wonderful. Thank you. All right, let me open this. Okay, great. Now I can still see your chat. Wonderful. All right, so can you see my screen?
Yes.
Yeah.
Okay, awesome. All right, so.
Actually, I only see like a sliver.
Yeah, we can only see the right hand, like a very sliver of your screen.
It worked for a minute and now it's gotten all messed up.
Oh, okay. So let me do that again. All right. Technical difficulties. Okay.
The slides are in the chat, so can you guys make sure you guys can get onto them?
Okay. So I hope everyone can see the slides now on the screen sharing. Yep. Okay, wonderful. So again, we wanted to spend the last lecture on concentration bounds. I hope we can finish them, but if not, the plan is that I will upload the slides and some, whiteboard written proofs if we couldn't finish the final description of the concentration bounds. But just to recap, we've already talked about concentration inequality for a random variable. So I won't be talking about information theoretical bounds since I've already uploaded the proofs and the descriptions to the website. So we will start with concentration inequality for some of random variables today. We will talk about concentration inequality for functions of random variables, okay? And we will talk about Martingale inequalities. And before that, I wanted to review a Martingale definition, of course, sigma algebra and these kind of concepts, right? So concentration inequality for some of random variables. So the most important concepts are two theorems, actually, theorem 3.1 and theorem 3.2, Hoeffding's inequality and Bernstein's inequality. So Hoeffding's inequality is used to derive the probability of the deviation, probability upper bound of the deviation for mean with some known range, okay? So you don't have to know the mean, of course. You just make sure that you know the range of these random variables. Now, theorem 3.2, Bernstein's inequality requires knowledge of the variance. However, because of the extra information, the additional information you have, you will get a tighter bound compared to Hoeffding's, okay? So let's see. What is the inequality of sums of random variables? Here is the Hoeffding's inequality. For random variables xi with a range, greater than equal to li, smaller than equal to ui, so lower and upper bounds. So the probability of this deviation, so what is the deviation on? Is on the sum of random variables, and that's essentially why we call it inequalities for sum of random variables. So the sum of random variables deviation from its mean, so expectation of the sum of random variables. This deviation, this is one-sided here, I'm writing. It's greater than equal to a, is upper bounded by this exponential function. What is this exponential function? The exponential power is 2a squared, so a is just the deviation, divided by the summation of the range interval squared. Okay, so so any question regarding like understanding of the theorem? Somehow I'm not able to see everyone on chat. Interesting. Or maybe Cal, do you want to remind me if there are some interesting questions on chat? I cannot see the chat, unfortunately. Don't know why. Hello?
So some people are asking.
Oh, Manas is here as well. Okay. Yeah, so let me see why I cannot see the chat. Yeah. Oh, I can see it now. Okay.
Okay. Okay.
All right. So, what am I looking? What is P and Q here? Oh, sorry, that's a typo again. Sorry, my slides, I was like, so busy making the slides, so I didn't double check this. So the P and Qs are lower and upper bound. So Q is the upper bound, P is the lower bound. So that should be UI minus LI, okay? I'll make the change when I upload the slides. Okay. All right, so here there is nothing about whether X being negative or non-negative, right? It is only a condition on X being within a range lower and upper bound, okay? So this is the Hoeffding's inequality. By the way, I wanted to emphasize that this inequality, don't forget there is a minus sign here. I don't know if you can see the minus sign well, right? So exponential of minus of 2a squared over this, sum of squares. Okay, so this is a decaying thing. So as so now the question is, as the number of random variables n goes to large, then would the probability, the upper bound of this be what? Exponential of this minus 2a squared over the sum of squares. It's gonna be very small, right? Essentially will go to 0. Exponential not go to 0, it go to minus infinity, right? Sorry, minus 0 actually. So here, the denominator is gonna be very large. Reason is that the summation of the sum squares n is very large, then the summation was gonna be large, right? Then this entire thing is gonna be very small. It's gonna be close to 0, right? Right, so even if you set the a to be a very small number here, then this entire thing is also gonna be small, right? So any
I have a question. Are you saying that the exponent is small or the right-hand side is small?
so I'm saying that if you have n to be very large, then essentially the denominator is gonna the denominator of the exponent is gonna be very large, right? And
Yes, and so the exponential will be small, and e to the 0 is about 1, right?
right.
Okay, that makes sense. Thanks.
Right. So now you can see theorem 2, Burston's inequality for random variables xi, where, of course, there is an additional condition, expectation of xi is going to be 0. And then the sigma squared, so the variance for each xi. So sigma squared is the average of the variance for each xi. All right. So then, as long as you know that the absolute value of xi is smaller or equal to an epsilon value, then for any a, you would have this probability of the sample mean of these random variables is going to be greater than equal to a, right? So this probability is smaller than equal to a to the power of minus na squared over 2 sigma squared plus 2 epsilon a over 3, right? So this, exponential is very hard to remember, but you wanted to, understand that this exponential basically is what? It's like my exponential minus na squared. So I wonder if there is a typo in the Hoeffding's inequality. Let me see. Is there a typo here?
I think it matches Wikipedia.
Okay, yeah. So, okay, I want to make sure. Okay, so the Bernstein's inequality here, you can see the exponential is minus of n times a squared. So if n is really large, I was hoping that this, so if n, oh, I see. Yeah, so if n is really large, then you can see here. If n is really large, then this exponential of minus very large, a very large, negative number is gonna be very close to 0, right? Do you see that?
Yeah.
Yeah, so if it's very close, if it is, very close to 0, then this probability of this summation greater than a is small, is almost 0. See? Right, of course, this a cannot be 0, of course, because we know that the expectation of these random variables are zeros. So let's say a is sufficiently large, then basically this means it will concentrate to a, right? So summation of the xi is going to be concentrated on a with a very high probability. And essentially the probability decays exponentially with the number of examples you have. Okay?
In the Hoeffding inequality, I think in the numerator it should be 2n square a square.
In the, which one? Bernstein?
In the Hoeffding inequality, in the
Okay.
numerator, it should be minus 2a square n square.
2a square n square.
No, I think that's only. And I think what you're seeing is that if the sum of the x's is divided by n, it would be that.
Okay, yeah. Okay.
Oh yeah, that's a good
Yeah,
point,
yeah,
right?
yeah,
So,
yeah.
if you have divided by n, then this range is gonna be also divided by n. So then it's gonna be like 2a squared n squared in the numerator.
Okay, yeah.
Okay. So indeed, if you have that, so that's a very good point. And that's why I was a little bit confused at first. So if you have this, right? Can you see what I'm writing here? Okay, so it's gonna be something like that, right? So then what this means is that this, the sample mean deviate from the expectation, it's gonna be up, it will also concentrate, right? So it won't deviate much from the expectation because this probability is upper bounded by a decaying exponential function, right? And it's gonna be very large here. So this will be like minus infinity, and this entire thing will be 0. So that's why I was confused, right? Like why when it's exponential of 0 is gonna be 1, so that wouldn't help us. Okay, does that make sense now? Okay. All right, so I will erase these. All right, so let's go to the next page. Did I forgot to say something? Yeah, so basically the Bernstein's inequality, I just want to emphasize that it's tighter than Hoeffding's due to the knowledge of the sigma squared, okay? So now I wanted to spend a little bit of time to, prove the Hoeffding's inequality. So it is actually a very interesting inequality to prove. So I think it's worth spending the time in class. So the proof sketch is very simple. You use the Chernoff bound to upper bound this probability of x greater than a. Why we cannot use others? Because we don't know more information about x, right? We only know the range. Using this exponential of e to the, power of tx, right? Remember the Hoeffding, also the Chernoff bound, we're using that. Now, you upper bound the exponential you upper bound the expectation of exponential tx for a random variable with expectation of x equals to 0. And then, so this basically is going to be Hoeffding's lemma. I will introduce the Hoeffding's lemma, but I just first wanted to give you a proof sketch. So you're going to upper bound this expectation of the exponential tx. And then thirdly, you're going to use this, independent random variables x1 through xn with this. So again, I guess I was gonna, I kind of interchangeably use Li and Ui, but really Pi and Qi, really what they mean is just the range of the random variables. So I will make the changes in my slides, okay, when I upload them. So let them xi and xn to be the independent random variables within the range Pi, Qi. Then probability of this, will be upper bounded by this exponential. This is nothing but this Hoeffding's inequality. So given this proof sketch, I will first introduce the Hoeffding's lemma. So what is Hoeffding's lemma? Let x be a random variable with exponential x equals to 0. Okay, so this is not about sum of random variables. This is just one random variable. You know that the random variable has an expectation of 0. Now the random variable takes value from a range p to q, right? So now for any t greater than 0, we will need to prove that expectation of e to the power tx is upper bounded by exponential of t squared q minus p squared divided by 8. So how do we do this? We use the whiteboard here. Okay, so first, okay, so first we know that exponential of x is a convex function, right? And we know that x, for any x within the range, let's say p, q, we know exponential of tx is gonna be upper bounded by this quantity here due to convexity. Right? What this means is that you have something like this. This is the P, this is the Q, right? So your X is somewhere within the middle between P and Q. So now you set your lambda to be Q minus X divided by Q minus P. Then 1 minus lambda is gonna be X minus P divided by Q minus P. So then using the simple convexity, you will get this equation, right? Questions? Oh, what I mean by lambda is like, remember the lambda you have in your convexity, right? So a function, if you take an average, anyway, so I don't need to define lambda, but I just wanted to say that this is nothing but due to convexity. Any questions regarding this? Okay, so that's that. Then expectation of e to the power tx is gonna be upper bounded by expectation of Q, right? This is nothing but taking the expectation, right? Because, you know, the random variables have that inequality, therefore the expectation should also enjoy this inequality. Now, how do you get that? So what is the expectation of this first quantity? It's gonna be Q minus P e to the TP. Why? Because expectation of X is just 0, right? Yeah, true. T greater than 0 is from the statement of the lemma, true. Right, so then this other quantity is gonna be minus P divided by Q minus P e to the TQ, okay? So this is again, just because expectation of X is 0, okay? So now, once we have that, then you can define this as exponential of phi t. So if you define that this way, then basically your phi t is gonna be logarithm of this quantity here. Okay, so then apparently you will see that this is gonna be TP, just simple math, e to the t of Q minus P, right? Okay. So far, is there any question? So for any t greater than 0, if you take a derivative with respect to phi, what do you get? You basically get P minus, it's gonna be Q minus P e to the minus of T Q minus P, and then this one, right? Right, that's the first derivative. Now, if you take a second derivative, again, it's gonna be alpha. So let me use alpha to denote this minus P, Q minus P, then this will be, yeah, I calculated this beforehand, so it's very simple math, so I don't want to do it online. Then this is a multiplication. Okay. All right, so this is very simple. You know, you don't have to worry about this for now. But this is nothing but just taking derivatives. Okay. So now, after that, we know that, you know, because phi of 0 is gonna be 0. Okay, and phi of 0 derivative is also gonna be 0. Okay. So now if you write it, if you set, again, u to be alpha divided by 1 minus alpha t to the minus. So if you do that, again, I change your variable. So you don't have to worry about the calculation. I'll tell you what this will be. So the second derivative is gonna be mu 1 minus mu q minus p squared, okay? So this is nothing but just simple calculus. So now we know, actually we can see that the mu is gonna be within the range from 1 to 0. Okay, so by the definition of these random variables, you will able to see that the range of the u is between 0 and 1 based on this definition here. Of course, recall that alpha is just minus p and q minus p. Okay, so this is easy to see. So basically, this means that u1 minus u is going to be smaller than equal to 1/4, right? Why is that?
It's max when mu is 1/2.
Right. Yeah. So now, so what are we saying? We will see that this phi second derivative is going to be upper bounded by 1/4 q minus p squared. Okay. All right. So now what do you see? So if you take the second order expansion of the function phi, you will see there exists, this is just Taylor expansion, such that, you know, the phi t can be written as, you know, you take the expansion at phi 0, so it will be t phi 0 derivative t squared over 2. Okay, this is nothing but the second order Taylor expansion. So then, you know, this is gonna be 0, this is 0, so it's gonna be t squared over 2. And then because this phi to the second derivative is gonna be smaller than equal to 1/4 q minus p squared, so okay. So what does this mean? This basically means that this, you know, so we recall exponential expectation of exponential tx, right? We're defining it as e of phi t. So this phi t is gonna be upper bounded by t squared over 8 q minus p squared. So then, you know, you get the Hoeffding's lemma, right? Basically, this thing is gonna be okay. So this is basically trying to, so just to recap the proof, you know, you have basically used the convexity of exponential family to come up with such a phi function, right? So the phi function is gonna be expectation of phi is gonna be expectation. So exponential of phi x, phi t is gonna be expectation of e to the power tx, okay? So if you come up with that, then what you do is you essentially do a second order Taylor expansion on the phi t to get an upper bound of the phi t. So essentially, this is the upper bound you get finally. Okay.
I have a question.
Yes.
So what happens with the higher order terms of that Taylor expansion, or do we know it's do we know that to be negative for some reason?
Oh no. So we said there exists a theta, right? Theta between 0 to t. So I'm not using 0 here. That's why.
Oh, okay, thanks.
Yeah, good point. Okay. So that's why we need to prove this term here for any second order derivative of phi evaluated at t is always going to be smaller than equal to 1 over 4 q minus p squared, right? So therefore, this term can be upper bounded. Okay?
Thank you.
Yeah, no problem. All right, so any questions? If not, then I'll come back to the slides. Right, so now using the whiteboard, we've proved the Hoeffding's lemma. So the Hoeffding's lemma is gonna bound the expectation of an exponential of tx, okay, using the range of the x. So this is actually a very interesting result. So, you know, so in your machine learning tasks, right, if you have a random variable, then, you know, if that random variable has a range, right, usually, for example, you would, you know, do a normalization, a pre-process of the data points. So usually the random variables that you work with will have a range, okay? So as long as you know that there is a range for this random variable, you can bound the expectation of that exponential of that random variable power tx, right? So essentially, it is going to be a function of t that is, you know, very intuitive, but the expectation won't grow faster than the exponential of t squared multiplied with the constant being related to the range of the variable. Okay, so now with that, we're ready to prove the Hoeffding's inequality, right? So first, what you do is you set the summation of the random variables as Sn. So that's usually a very popular notation for setting the summations of random variables. Now, you need to bound the probability of the deviation, right? So now this is not like a normalized summation. It is just the summation itself. So as some of you noted, it's not divided by n here. So the probability of Sn deviate from the expectation of the sum is greater than equal to A, right? So essentially this A will be boosted by like an n parameter, right? If you have a deviation for each of the random variable, then you're summing over all the deviations here. So A is actually the summation, right? So this probability of this deviation is gonna be smaller than equal to e to the power minus ta and exponential of this e to the power Sn minus ESN. So why is that? I actually, you know, hinted this during my proof sketch.
So because of the lemma you proved, because that
Is
on
that
the
true?
left-hand side has an expected value of 0, right?
Is that true? We're just using chain of bound, right? The first thing. Do you see?
Oh, okay, right, thanks.
Yeah. Right. So I kind of hinted it during my sharing of the proof sketch. So you're getting a chain of bound using this. Using chain of bound, you're getting this inequality. And now, how do you get this step? This is a simple one. Any ideas?
You just
Yeah.
pick up the f sub n variable into its individual
Yes.
x sub i's.
Yes. Independence of the xi's, right? Wonderful. Now, how do you get this one?
The lemma.
Yes. which we've already proved, is a very interesting lemma. It bounds the random variable expectation of e to the power tx with the expectation of t power t squared range squared over 8. Okay, so now how do you get this one? Nothing but just the property of the exponential function, right? Do you see? So this is a constant with respect to the product from 1 to n. So it is irrelevant to the product. So I can take this out, and you're just using the property of the exponential function. So now basically you get this thing. So this is very important. The following step is very important. What is this telling you? This is telling you that, you know, I get a upper bound, but this upper bound is a function of t, right? Which confuses me. So now the function of t, what would you do? Right? Because you wanted to minimize the upper bound. As I said, the loose upper bound is not preferred. You want it to be as tight as possible. So you wanted to minimize that upper bound as much as you can. And that's why you are essentially choosing t that minimize this bound. How do you do that? You essentially just take the derivative and set the derivative to be 0 and solve for it. Basically, you'll get this t equals to 4a divided by summation of the range squared. Okay?
So I have a question.
Yes.
In the step after taking the product, when you have e to the minus ta, wouldn't that be repeated n times because you're taking the product n times with that? So wouldn't that come out as e to the minus tan?
Oh yeah, I think there's a typo. This thing should be outside of this, you know, here.
Oh, right.
Yeah.
Okay.
So that's a typo. Very good point. Okay. Right. So when you do the independence of x, you wanted to take this out first, and then this thing will become a product of these the following things, right? So I mean, I'm making this very messy here. So it should be.
I had a question about normalizing random variables.
Okay.
Can you actually do that? What if you were trying to model something like stock price or an asset price? Then if you just assumed it would be in some range, is that what you would do?
What price did you say? Yeah, usually you would assume that the random variables you deal with are within some range. For example, if you are dealing with images, right? So the pixel values are usually within a range, right? Sometimes.
Yeah, that wouldn't make sense. But for a stock, to assume it won't go over some number, like I'm not sure.
Yeah, for a stock, then that's another question, right? So yeah, sometimes you cannot have a limit for the stock prices, right? However, you might wanted to make this assumption that these variables have an upper bound. Usually, if you don't have an upper bound, things will get crazy. And many of the theorems won't work. So actually, when I talk about optimization, you will see, the function value upper bounds are very important for proving, the convergence of non-convex optimization, convex optimization, and so on. Okay.
Could you maybe just get away with it by choosing a very high upper bound in that case? Like something that
I would
wouldn't
say
be.
in practice you can do that.
Okay.
I think that would just your inequality would be pretty irrelevant if you just use some very high bound.
Yeah, that's true. Exactly. So you can see that the tightness of this inequality depends on the range, right? As you can see, if the range is very large, it won't be very tight. See?
Yeah.
So that is basically, this is not a conflict. This is actually a very intuitive explanation you can imagine, right? If you don't know anything about a random variable, the range could be very large, and you don't know the lower and upper bound, you can have a very rough estimation. Then you won't get a very tight concentration bounds, right?
Right.
Because
Yep.
these concentration bounds are telling you how good you can estimate these means, how good you can estimate the sample means or the summations, right?
Yeah, that makes sense.
So, in that sense, if you don't know anything about this random variables, you cannot do much. Okay. So I didn't give the examples for these reasons. I think we've seen some examples for the previous inequalities for random variables. Now you can imagine doing summations of these and applying these inequalities. So I don't want to repeat those, but similarly, these examples should apply here. Now we're ready to go to the concentration inequality of functions of random variables. So we have two theorems. Hoeffding's inequality. So it's bounding variance, and McDiarmid's inequality is bounding the deviation of functions. Okay, so we'll see what they are. So the Hoeffding, again, that's the typo. Hoeffding's inequality is you have an S that is mapping from Xn, so to the R. Okay, so Xn is just what? It's just a bunch of random variables, n random variables. From that to R, the real space. So you want S to be a measurable function, okay? Invariant under permutation. So you can permute these random variables, and no matter how you permute it, the result of that function is always going to be the same, right? So you let the random variable z be given as, the output of that measurable function. So z equals to s of x1, x2 up to xn. And of course, you can permute these x1, x2s, right? Because it's invariant under permutation. So then the output z have a variance that is upper bounded by 1/2 summation of the exponential of the z minus zi prime squared. So what is zi prime squared? The zi prime squared is the replacement of the xi using xi prime. And xi prime, what is xi prime? It's just another sample from the same distribution. So what does this mean? It basically means that you can replace any of these for a set of random variables x1 to xn. You can replace this with another sample from the same distribution, and then the output of the z is gonna be the zi prime is only like a replacement of one coordinate here. Now, if you take the expectation of the difference squared, what does this tell you? This will tell you that under this replacement of this one single variable xi, what is the difference of your output of the function? Okay, so the difference of the output of the function squared, expectation of the squared, and taking the summation is going to be the upper bound of the variance of the z. Okay.
So is there a typo on the first line? Should be S colon RN to R, and then also on the
no, it should be X. It should be X and to R because you're taking the how to say. So what I mean is like the X is gonna be like the support of these random variables X, right? So Xn,
Oh, okay.
X power n is just
Okay, if it's the support, yeah.
Mhm.
And then is that the same for F from UM under theorem 4.2? U is the support, U to the M is the support of those X1 to XM.
Yeah, so let's see, right? So, we have X, so McDiarmid's inequality is that we have X1 to XM be independent random variables taking values in U. So that's the support of the space of the X, right? So, the F is gonna be a function mapping from the power, space power M. So it's like, the space of the M random variables, X1 to Xn, to the real, be a function such that for all of these variables, right? So the supremum of this difference between these function values. So there is again, I think there is a typo here, right? There is a prime, I believe. So the difference between these two is gonna be, the supremum of that is gonna be upper bounded by Ci. So if that's the case, then for all epsilon greater than 0, the probability of the deviation, so the deviation probability is going to be upper bounded by this quantity here. So this is very much like a Hoeffding's inequality. However, this is on the function, right? You can see that the function has this, kind of like a range property. You can see that, right? So before it was saying like, that, in Hoeffding's inequality, you're saying that random variable taken value from, a lower bound and an upper bound, between the lower and the upper bound. Here you're saying the supremum of the difference between the function value will be upper bounded by the Ci upper bound here. Okay, so it's basically like no matter, changing just one coordinate, changing just one variable, the function value would not change for more than Ci, right? So this is actually a widely used inequality here, this McDiarmid's. So it is very much similar to the idea of like the Hoeffding's inequality, but it's on a function value. So as long as you're able to establish this, upper bounded changes in the function value by replacing one variable, then you should be able to get this concentration bound. Okay. All right. So any questions before we move on to Martingale's inequality?
Sorry, what was the CI in the previous slide?
It is a constant, right? This is, such, if you were able to have a function f such that the function value difference between replacing one variable with xi with xi prime. So no matter how you do that, as long as, you replace one variable and the function value change won't be, the absolute value of the function value change won't be more than Ci. So Ci is a constant.
Okay, got it. Thank you.
Just like in Hoeffding's inequality, you have the range x greater than equal to Li and smaller than equal to Ui. But now, because the object that we are looking at is a function, so you are thinking about the function on a bunch of random variables.
Okay, and these are potentially M bounds, right? Like C1, C2, all the way to Cm, right?
Yeah.
Okay, thanks.
Okay. Oh, sorry. So Ci is not just the best constant, by the way, Michael. So Ci is gonna be like, C1 for replacing x1, C2 for replacing x2, and so on, right? Of course, you could also think that it is the best bound you can get. So then it's gonna be C. So then this thing is gonna be 2 epsilon squared this exponential would be 2 epsilon squared and c squared multiplied with m, right? Something like that. Yeah, okay, wonderful. All right, so Martingale's inequality, before we go to Martingale's inequality, I wanted to motivate why we need martingales. And some of you might not remember the definition of martingales. For the definition of the martingale, we need to recall the elements of probability. So the probability space. What is the probability space? There are 3 very key elements, 3 very important elements for the probability space. First is the sample space, omega, okay? So it is the set of all the outcome of a random experiment. Okay, so it's the sample space. Now you have the event space, sigma, which is the set whose elements, basically an element of this event space is gonna be an event. So whose elements are subsets of the omega. Okay. Actually, last time when we were reviewing this, I didn't mention there are very important properties for an event space. So the event space has to include none, okay? And also, if you have an event that is in event space, then the complement is also gonna be in that event space, okay?
Is there a typo here on the 3rd bullet where it says summation I1 to 0 n there?
Oh, 1, yes, true, good.
No, the summation should be deleted, and this should just be union I from 1 to n, or infinity.
Let me see, so.
It's not like a sum, it's like a.
Oh yeah, it's a union, right? So it's a limit for the union, right? So it's union I from 1 to n.
Yeah.
Okay, yeah. So, right, so the 3rd one is like, as long as you have, for any events within this event space, the union should also be in the event space, okay? So the 3rd key element for probability space is the probability measure. Okay, so it's a function P, so that's gonna be a probability measure. It maps the event space to the real, right? So it has to satisfy these properties. We emphasize this, so I don't need to say that again. But more importantly, I wanted to just recall the concept of sigma algebra or sigma field. So an event space, sigma is a sigma field on the sample space omega, right? So first, let's understand the event space better. So if you have P of omega, so this is the power set of omega. So what is the power set? It is just the set of all subsets of omega, right? Now with that, we see that if sigma is a subset of the power set, basically means that sigma is a subset of the P of omega, then sigma is gonna be a sigma field on omega. Okay, so this is the definition. For example, you can imagine that if you have an omega, which is like the sample space, A, B, C, D, so that's the set. Now, one possible sigma field on the omega is gonna be F, right, so this is gonna be sigma, sorry, sigma. Sigma equals to the set of null and AB, CD, and ABCD. So you can check whether this is true, right? I claim that this is a sigma field, and you can see whether this is true. So the 3 properties.
I think there's another typo on the 2nd line. So I think it has to say sigma is a sigma field only if it satisfies those 3 properties.
Which line? Can you say that again?
Yes, on the 2nd line, it
Here.
should say sigma is a sigma field on omega only if it satisfies these three properties.
Oh yeah, true. Yes, yes. Right. Yeah, I didn't finish writing that, but you have to satisfy these three properties. Okay. So you can see here, for example, the null is included in this set sigma, right? AB is included. Now you can check whether the complement of AB is included. So the complement of AB is just CD, so it's also included. Now the omega itself is also included. Reason is, if now is included, the complement of now is just the omega. So omega has to be included. So apparently this is a sigma field, right? You can imagine that, for example, this won't be a sigma field, right? Because this complement of AB, which is CD, is not included. All right. So now, what is the sigma field generated by a random variable? Basically, recall the probability space if you have, the sample space, the event space, and the probability measure P. Then the random variable is basically defined, is defined as a measurable function X that is mapping from the omega sigma. So omega is the sample space, sigma is the event space, or you can imagine sigma is actually also a sigma algebra here. So this two is mapped into Rn and this Borel set of Rn. So of course, if you imagine this n being 1, then it's going to be a random variable. If n is greater than 1, it's going to be a random vector. Okay, so this is definition of the random variable. So what is basically this is saying? So so let's explain this a little bit. So you have an omega. Omega is your sample space, right? So you kind of map that into Rn space, right? So sigma is kind of the events, the event space. And the events have to be mapped into like a measurable, so it's gonna be like B of Rn. So the Borel set on the Rn, right? So this X has to be measurable with respect to the sigma field. So X is measurable with respect to this sigma here. Okay, so this is just a recall of the random variable definition. Now, so what does that mean by the sigma algebra generated by X, the random variable? So basically it means that it is the collection of this pre-image of the random variable. Or you can imagine it's the pre-image of the Borel sets. Okay, so X inverse B, and so, B is just from the Borel sets, right? So it's something that is mapped already, using this mapping X, right? So B is just the element of the Borel sets. So you get a X inverse of B. So it's the input, is the pre-image of the X, right? So that means it's gonna be the sigma algebra where you use to define X, okay? So the definition is clear, but there is a subtlety here. So, I just wanted to very quickly, talk about this. Maybe this is a little bit confusing. The subtlety here is that in practice, the pre-images of the Borel sets may not be all of sigma. So, instead they may constitute much coarser subset of it. So, for example, if you define the sigma prime to be this, so this is basically like, as long as S is belonging to this sigma here, but S is the pre-image of the X inverse of B, it won't be the entire set of the sigma. It could be a subset of the sigma. So it is still a sigma algebra, but it is the smallest sigma algebra that makes X a random variable. So what does this mean? This basically means that the sigma field generated by a random variable is actually the smallest sigma field that makes X a random variable. Okay, so if it is very confusing to you, then you just only need to remember this. Okay. So now we're ready to see what is the definition of the Martingale. So Martingale is a sequence of random variables. So it's a stochastic process for which at a particular time, the conditional expectation of the next value in the sequence, given all prior values, is equal to the present value. So this is especially relevant when you're thinking about a stochastic process and you wanted to predict the next expectation of the process, given the history. Okay, so Martingale process is definitely very useful in, for example, optimization, right? So a lot of you are interested in optimizing a non-convex function, right? Which is the foundations of, learning in deep neural networks. So now it actually becomes very complicated, but Martingale will definitely help you in terms of analyzing that, right? So we call the conditional expectation for a random variable x, y. So can someone tell me the difference between expectation of x given y equals to y versus expectation of x given y? Of course, x and y, the capital X and y's are random variables, whereas the small y is just a value, a realization of the y. All right, first I wanted to ask, what is this? Is this a value or is this a random variable? Yeah, David already gave us the answer, right? So the first one, because you are conditioned on a realization of y, then the expectation of x given the realization of y is gonna be a real number, right? It is nothing but an expectation. It's the conditional expectation when y takes the value y, when capital Y takes the value small y, right? Whereas the second one, you don't really specify what's the value you're taking for y. Therefore, it is itself a random variable. It should be a random variable that is dependent on y, of course, as well as x, right? All right, so kind of, I wanted to give you a very interesting, this is actually from Wiki page. I think this is an interesting history about the Martingale. So basically they're saying that originally Martingale is referred to as a class of betting strategies that was popular in the 18th century France. So that was kind of interesting. You can see that. So the simplest of these strategies was designed for a game. So what is the game? The game is that the gambler wins their stake if a coin comes up heads and loses it if the coin comes up tails. So this is a very simple strategy, right? A simple game. Now the strategy had the gambler basically double their bet after every loss, right? So you can see they will double the bet after every loss so that the first win would recover all previous losses plus win a profit equal to the original stake. Okay, so if you think about this looks very, interesting game. It seems like you could, have a chance of winning, right? So basically, they're saying that as the gambler's wealth and the available time jointly approach infinity, our probability theory says that the probability of eventually flipping heads approaches 1. So it's like, it seems like if you play long enough, you would always win, right? However, basically this is just makes the Martingale betting strategy seems like a sure thing, but the thing is the exponential growth of the bets, because you are going to double your bet. So basically your bet is going to be exponentially growing, right? So basically the exponential growth of the bets eventually bankrupts its user due to finite bankrolls. So you only have finite resources you can bet. So basically, the wiki page says that the stopped Brownian motion, which is a Martingale process, can be used to model the trajectory of such games. So that's kind of one motivation how we can use martingales for gambling. But in modern machine learning, you can use martingales for a lot of interesting things, including game theory, including optimization. Okay, so today I wanted to introduce very important martingale concepts, and maybe actually next lecture, since we are already running out of time, next lecture I'll also very briefly talk about the martingale inequality that we will use, right? So I will use the next 4 minutes to talk about some examples of martingale. So I wanted to first talk about a special case. So it's called a dupe martingale. What is a dupe martingale? So let's say you have a sequence of independent random variables. Okay, so independent is very important. So x, k from 1 to n. Now your fx is just denoted as a function taking input x1 through xn. Okay, so fx is just that. So we didn't specify what is fx, but we only know that fx is gonna map Rn to R. Now the goal is you want to obtain bounds of the deviation of f from its mean. How do you do that? So the method, what you can do is you're going to do the following thing. You're going to set the y0. You're going to construct a new sequence of random variables. The new sequence of the random variable will be y. So y0 will be the expectation of fx, okay? And yn is gonna be f of x. So somehow this important thing here is that this conditional expectation, this yk is gonna be expectation of fx conditioned on the history of x, okay? So what does this tell you? This basically tells you that the sequence that you construct is getting more and more fluctuations, right? So y0 is just a scalar, it's a value. Why? Because it's just expectation of the fx, so it's gonna be a value. Whereas yn is just fx itself, so it is a random variable. It fluctuates a lot. So basically this construction of the sequence of y is more and more, you're gaining more and more fluctuation, right? So that's the intuition here. So the Martingale approach to tail bound is based on the telescope decomposition. What do I mean by that? So if you look at the difference between fx and expectation of fx, you will see that it actually is just yn minus y0. Okay? Right? This is by definition. And
I
now,
have a question.
Yes.
So here f is a function from Rn to R or Xn to R?
Oh yeah, so you can say xn to R, but yeah, so but xn could be also taking values in R, so it is also fine to just say Rn to R.
And here yn, you said yn is a random variable, but if f is from Rn to R, then fx will be a real number, right?
Yes.
So how is yn a random variable?
Oh, no, so sorry. Fx is gonna be also a random thing, right? It's a random function because it depends on the random variable x1 to xn.
Okay.
Yeah, so it still has randomness in it, right? Okay, so just, I just wanted to finish this slide. So the difference between fx and expectation of fx can be written as y0, yn minus y0. Why? Because of the definition, right? You're just defining yn to be that way. Now, the very interesting thing is that if you set the yk to be expectation of fx conditioned on the history of x, then this difference could be decomposed as the telescoping sum, okay? So you can see the telescoping sum is just summation of the differences of the consecutive ones, right? So yk minus 1. So these are two neighboring random variables you construct, okay? Right? Because all of them will cancel out except for this yn and y0. Now, interesting enough is that this yk is gonna be a particular example of a Martingale sequence, and we call it Doob Martingale. Oh, right, so now I'm ready to introduce the definition of the Martingale sequence. So let's say if you have a sequence of sigma fields that are nested. So we've already introduced sigma fields. Now Fk is a sigma field. So it's an event, you can think of it as an event space. It's the minimum event space for a random variable, okay? So, you know, just for simplicity, you can think about it as an event space. Now, Fk is gonna be a subset of Fk plus 1, known as a filtration. Okay, so this is just the definition of the filtration. It's just like, you know, a sequence of sigma fields that are nested. Now in Doob Martingale, the sigma field essentially are the sigma field of x1 through xk. So it's the event space of these random variables x1, xk. Or you could imagine that in practice, you can just think about them as the random variables themselves. So generated by the first k variables play as the role of the sigma field. Okay, so then the yk is gonna be a sequence of random variable measurable with respect to the sigma fields respectively, which is known as yk, k from 1 to infinity, is adapted to the filtration. Okay, so finally, we're ready to introduce the definition of the Martingale sequence. It is just given a sequence yk of random variables adapted to a filtration. So what does this mean? Basically means that, you know, it is adapted, it is measurable. This yk is measurable on these sigma fields generated, you know, generated from these fk's, right? So the pair yk fk is a Martingale if for all k greater than 1, the expectation of the absolute values of the yk is upper bounded by infinity. So it is a, you know, it's a bounded value, and expectation of the conditional expectation of this yk plus 1 condition on this filtration, oh, sorry, not filtration, condition on the sigma field is equal to yk. So the future, the condition, the expectation of the future conditioned on the history, it is related to the current value yk. Okay, so here, this is a random variable. This is also a random variable, but somehow you can establish this equality here. So that's the power of the Martingales. So we don't have time to finish talking about it, but I will spend a little bit time talking about Martingales next lecture. So next lecture on, we will talk about the Martingale difference sequence, and we'll talk about the sum of Martingale difference sequence, Azuma's inequality. So there, after that, we'll start to talk about the provably approximately correct theorems there. Okay. So because, and finally, with the, you know, definition, or with the understanding of the concentration bounds, we should be able to go to the sample complexity study of this So there, it is more closely related to machine learning concepts. Here, we're still talking about like these concentration bounds, which are more, closely related to math concepts that are foundations for these sample complexity theorems. Okay, so if there is no more questions, then this is the end of today's lecture. Okay, I will make sure that the typos in the slides will be corrected. All right, thanks everyone.